Welcome to the deep dive. Today, we're getting into multiple regression analysis.
Hmm.
Forget that simple one cause, one effect thing. We're looking at how, a whole team of factors shapes an outcome.
Right.
You want the insights fast, and that's what we do. We'll break down the core ideas here, showing how it helps understand those complex data relationships.
Exactly. Simple regression, it's like saying, okay, one ingredient makes the cake.
Yeah.
Multiple regression gets it's the flour, the sugar, the eggs,
Mm-hmm.
everything working together.
Okay.
And that immediately brings in some, well, new challenges compared to just looking at one thing at a time.
Right. Okay. Unpack that.
Yeah.
So if we have all these ingredients, these
Yeah.
variables, how do we even figure out what each one's actually doing? Like those coefficient numbers.
Well, what's really key here is that each coefficient tells you the impact of just one ingredient, one independent variable on the final result, the dependent variable, right? But, and this is the crucial bit,
Yeah.
it assumes all the other ingredients are held constant.
Ah,
That holding others constant part, that's the big difference from simple regression. It's like, trying to figure out the effect of just the sugar keeping the flour and eggs the same.
got it. Isolating the unique contribution. So we know R squared tells us how much variance we explain, sort of how good the overall recipe is.
Yeah.
But then there's this adjusted R squared. What's that about? Why the adjustment?
Think of it like this. R squared. It gets a bit too enthusiastic.
Mm,
It almost always goes up when you add any new ingredient, even if that ingredient doesn't really add much value.
right.
Adjusted R squared is, let's say, more critical. It actually penalizes the model for adding predictors that don't improve it significantly.
Ah.
So it gives you a more honest measure of model fit, especially if you're comparing models with like different numbers of ingredients.
That makes total sense. Finding the most effective combination, not just the biggest.
Okay, now, what if some ingredients are really similar? Like using brown sugar and white sugar, is that the multicollinearity thing? That's a perfect analogy, yeah.
Hmm.
Multicollinearity is exactly that. When two or more of your predictors, your ingredients, are highly correlated, they're too similar.
And the problem is,
Well, the problem is if you have two very similar sugars, it becomes really hard for the model to tell which one is actually responsible for the sweetness.
okay.
It kind of messes with the coefficient estimates, makes them unstable, and clouds our understanding of each one's individual impact.
So how do we spot that? How do we know if our ingredients are too alike? Are there checks?
Oh, absolutely. We have diagnostic tools. A common one is the variance inflation factor,
Yeah.
VIF.
Yeah.
Yeah, a high VIF score for a variable basically signals, hey, this predictor is pretty similar to some others in the model. It flags that potential multicollinearity issue.
Okay, VIF checks for similarity.
Yeah.
Now, with simple regression, we look at a p-value to see if our one variable matters.
Mhm.
Is there an equivalent for the whole model in multiple regression? Like, is this entire recipe doing anything useful at all?
Yes, exactly. That's the job of the F-test. The F-test assesses the overall significance of your entire model,
The whole thing.
the whole thing. It tells you if at least one of your independent variables is significantly related to the dependent variable.
Mm,
Doesn't pinpoint which one, but it says, okay, this model overall has some explanatory power.
interesting. So the F-test is the big picture verdict. Now, what if the effect of one ingredient actually depends on the amount of another? Like maybe more flour needs more eggs to bind properly. Is that where interaction terms come in?
Precisely. Interaction terms let us model exactly those kinds of synergistic effects. You create a new variable, usually by multiplying two existing ones,
Ah,
and it allows the effect of, say, flour on the outcome to change depending on the level of eggs. It adds, well, a lot more nuance because things in reality rarely work in complete isolation.
right. Things interact. That sounds like it could get complex fast. Speaking of which, I saw stepwise regression mentioned. Is that like a shortcut for finding the best variables? Sort of. Stepwise regression is an automated method. It algorithmically adds or removes predictors based on certain statistical criteria, like p-values or AIC.
Okay.
It tries to build the best model automatically, but it's a bit controversial. Relying solely on the algorithm can sometimes lead you down the wrong path or miss important theoretical relationships. So, useful, maybe, but handle with care.
Good caution.
Yeah.
Sometimes the chef's intuition still matters.
Yeah.
Now, are there fundamental rules, like assumptions we need to check when we build these models?
Oh, definitely. Multiple regression rests on several key assumptions for the results to be valid. Things like linearity, The relationship between predictors and the outcome should be linear.
Okay.
Independence of errors, each observation's error term is independent. Homoscedasticity, the variance of the errors, is constant across all levels of the predictors. And normality of residuals.
Wow, okay. Why are they so important? Well, if these assumptions are violated, our coefficient estimates might be biased, the standard errors could be wrong, and our p-values might not be reliable. Basically, the model's conclusions could be misleading.
Got it. Check the foundations before trusting the house. So last thing, if we have a couple of different multiple regression models trying to explain the same thing, how do we compare them? How do we pick the best one?
Good question. We often look back at adjusted R-off higher is generally better, but keeping model parsimony in mind.
Parsimony, like simpler is better.
Exactly, if it explains things well. We can also use F-tests to formally compare nested models where one model is a simpler version of another. And critically, we examine diagnostic plots like residual plots to see how well each model meets those assumptions we just talked about.
Okay, so it's a combination of fit, simplicity, and checking those assumptions. We've definitely gone from a single ingredient to quite the complex recipe here.
Absolutely. It's a big step up. But multiple regression gives us that much richer, more realistic view of how the world often works with many factors interacting.
Yeah, it really forces you to think about the whole system.
Mm-hmm.
Right. So for you listening, thinking about all this complexity, these interacting factors, what real-world things do you now see differently? Not just as A causes B, but maybe as A, B, and C influencing D. Where do you see that recipe of influences? Something to think about. Thanks for taking this deep dive with us.